I think there are many of you in the audience who know this material, many of you more expert than I, and I hope you'll bear with me during the parts of it that is familiar to you. The talk will be on Hodge theory and algebraic cycles, and in outline, what I'd like to do is first just recall the classical theory, essentially the classical invariants of an algebraic cycle, the Deligne class, and then review or at least three of the basic conjectures, the Hodge conjecture, the generalized form of it, the Bloch-Beilinson conjecture, and a conjecture of Grothendieck, and then talk about some implications of those basic conjectures, or at least parts of them. If they are true, what algebra geometric consequences do they have? In particular, I'll talk about an extension of the classical theorem of Abel, which is where Hodge theory really began, and then some more speculative remarks on what are called extended normal functions. So to recall the classical theory, one studies a smooth projective algebraic variety defined by polynomial equations. And for later purposes in this talk, the field of definition of the variety will be of importance. So we'll just think of the variety as defined by polynomials whose coefficients are in finitely generated subfield of the complex numbers. The geometry of an algebraic variety, as I think you know very well, is reflected by the configurations of subvarieties lying in the variety. Classical pictures are collinear points on a cubic, lines on a quadric, and things that are more difficult to draw. Historically motivated by many things, but in part by relations such as I've written here on the divisor of a meromorphic function on a compact Riemann surface, or the same thing as a smooth algebraic curve, one was led to consider the group of algebraic cycles. The group of algebraic cycles is the group of formal linear combinations of irreducible algebraic subvarieties of codimension P with integer coefficients. And again, motivated from the classical theory, studying divisors of rational functions on an algebraic curve, one is led to introduce an equivalence relation. This group is too big, it's not manageable, of rational equivalence, which, roughly speaking, it's generated by saying that two cycles are rationally equivalent if one can be moved to the other by a one-parameter family parameterized by the rational line. Okay. So that's written here. And then the cycles modulo rational equivalence, that quotient group is the Chow group, one of the basic objects of study, probably the basic object. That and the higher extensions, the higher charge groups defined by Bloch, are probably the basic objects from some points of view in the study of algebraic cycles. So algebraic cycles modulo rational equivalence are the Chow groups. Now again, classically, one studied configurations of points on an algebraic curve by means of abelian integrals or abelian sums. This is where the subject began with the theorem of Abel, and that led to the following picture, that there are two invariants of a divisor on a compact Riemann surface. The first is the degree, and 4 cycles of degree 0, so they're boundaries of one chains. You do these abelian sums. So that maps the kernel of the map taking a cycle to its degree. It maps the kernel of that which for later use I've denoted by sub 1 there, to the Jacobian variety of the Riemann surface, viewed for the purposes of this talk as linear functions on the holomorphic differentials modulo the lattice generated by periods. And because I'm going to be talking about an extension of this, let me just recall the classical version, the classical Abel's theorem. It maps cycles that have degree 0 to the Jacobian by abelian sums, as mentioned on the previous overhead, if one considers that mapping. Then the original form of Abel's theorem in modern language was the divisor of a rational function maps to 0. A rational function, the divisor has degree 0, same number of zeros as poles, and under the mapping to the Jacobian, it goes to 0. And then there's a converse to Abel's theorem that any divisor of degree 0 that goes to 0 in the Jacobian is a divisor of a non-zero meromorphic function. Now, in general, these two invariants of, in this case, divisors on an algebraic curve will be combined in, or should be combined into what's called the Deligne class, mapping the child groups to Deligne cohomology. The graded pieces of that are the ones that I'll be focusing on today. So I'll concentrate mainly on the sort of more classical invariants than the Deligne class, the graded pieces of that. And to recall what those are, if you have a smooth projective variety, or more generally a compact Kähler manifold, or more generally, you can have just an algebraic variety, not necessarily projective, but smooth, according to Deligne's mixed Hodge theory. The cohomology has the well-known Hodge decomposition. For an algebraic curve, the first cohomology are the holomorphic differentials, direct sum their conjugates. And in general, you have the Hodge decomposition on cohomology. Or you can describe it alternatively in terms of the Hodge filtration given by this equation here. Okay, so that's the Hodge structure on the cohomology of a smooth projective variety, or more generally a compact Kähler manifold. The groups to which algebraic cycles map, again classical, are first the Hodge group. Those are the integral classes because an algebraic cycle is a geometric object. It's an integral cycle topologically. And it's of type PP, first noticed by Hodge in general. It had been noticed in special cases earlier. And the intermediate Jacobian, which I'll think of as linear functions on the first half of the Hodge filtration in a certain degree, modulo the lattice generated by periods. Then there are maps from the child groups to the Hodge group. That's the fundamental class. And the kernel of that maps to the intermediate Jacobian by the Abel-Jacobi map. These are the graded pieces of the Deligne class. The classical Hodge conjecture, stated by Hodge just a little bit over 50 years ago, was that the fundamental class is surjective. That is, a Hodge class, something here, is always in the image of the fundamental class map. It comes from an algebraic cycle. The status of the Hodge conjecture, it's classical, going back now 80 plus years, for codimension 1, for divisors due to Lefschetz. And there are two proofs that I know of. One is the proof given by Kodaira-Spencer. The Kodaira-Spencer proof has two steps to it. The first step is a Kähler step, that if you have a Hodge class, then it's the first Chern class of a holomorphic line bundle. That comes from the exponential sheaf sequence, which is only valid in this form in the analytic setting, so the analytic topology. And the second step is what's called Gaga, the comparison theorem between analytic and algebraic, that says that the group of line bundles of X as an algebraic variety is isomorphic to the group of line bundles considered as an analytic variety. So it's some extension of Chow's classical theorem that an analytic subvariety of projective space is algebraic. So looking into higher codimension, Attier and Hitzebruch found examples of torsion classes, which are automatically then Hodge classes, which are not algebraic. They don't come from algebraic cycles. So the theorem is false for torsion, so it should be reformulated modulo torsion. More recently, Kolar has given an example of a class, an integral class, that is a linear combination of algebraic varieties with rational coefficients, but is not a linear combination with integral coefficients. So to speak, it's an integral class that's algebraic over Q, but not over Z. So you really need to take torsion out of the formulation. The Kähler step here in the Kodaira-Spencer proof is, I would say, very false in higher codimension. There's an example due to Claire Voisin of a four-dimensional complex torus having a Hodge class in the middle dimension and no geometry whatsoever other than what comes from points. So no coherent sheaves other than ideal sheaf of points, no vector bundles, no cycles. It's very barren as a geometric object. So I think, to me, that suggests that when one is thinking about these problems, you really need to first have a process that takes out the torsion and makes use from the beginning of the fact that you have an algebraic variety. There are some interesting examples of the Hodge conjecture for special varieties, for Fermat-type varieties, going back to work of Scioto and others some years ago. And they're consequences of the classical theorem. But I think, as far as I know, there's no general construction of cycles in higher codimension. So from now on, today, I will do everything modulo torsion. The generalized Hodge conjecture, which I'm not going to formulate precisely, but roughly speaking, it says that if you have a cohomology, if you have a sub-Hodge structure, so you have a Hodge structure, a sub-Hodge structure is given by a sublattice that's compatible with a Hodge decomposition. You think of it as vanishing in the Hodge decomposition from the ends. Then that should be supported on an algebraic subvariety whose codimension reflects how far in you've come in the Hodge decomposition. Right, so sub-Hodge structures are supported on subvarieties, the extreme case being the Hodge conjecture. Turning to the Abel-Jacobi map, examples of Clemens from, again, the early 80s show that the image, which always has countably many components for sort of easy reasons, may in fact just be countable itself, but not finitely generated. So it's a non-finitely generated countable group. So that's the image. The kernel, examples going even further back, beginning with David Mumford and then done by many others, showed that the kernel of the Abel-Jacobi map may be infinite dimensional. Mumford showed it was infinite dimensional for any surface which has non-zero holomorphic two forms. Some order, at least in my mind, was brought to this picture by conjectures of Bloch and Beilinson, which for today's purposes I'll phrase this way, that there is a filtration on the Chow groups. And again, everything is modulo torsion, with the following properties: that the associated graded are described Hodge theoretically, that the first two steps in the filtration are the classical kernels of the classical maps, fundamental class and Abel-Jacobi map, that the filtration terminates at p plus 1. And finally, and for today most importantly, that if the variety is defined over a number field, then when you look at the Chow group of cycles defined over that number field, the filtration already terminates at the second level. As far as the status of this goes, I think, again, there are people here much more expert than I. There are proposals for what the filtration should be in general, due to Mura, Janssen, and perhaps others. There's a motivic proposal for what the Hodge theoretic quotients should be, how they should be described due to Bailenson. And as far as the fourth part, I'm aware of a few special examples. The one that strikes me especially is due to Bloch and Suslin, which is a degenerate quartic. It's as if you wanted to study elliptic functions in the very beginnings, but you didn't know elliptic curves, you degenerate them into C star where you have just periodic functions. Here, one doesn't really know the Chow group of a Kummer surface, a quartic, but if you degenerate it to a tetrahedron, then you have a very nice story due to Bloch and Suslin. I'd like to comment briefly on some of the arithmetic properties of algebraic integrals. These are periods in the sense of Kontsevich and Zagier. Think very classically. You have an algebraic function defined by polynomial with coefficients over Q or in a number field, and you integrate it. And this was a much studied object during the century, beginning the work of Siegel, and finally the theorem that Siegel was working on was proved by Bombieri in the early 80s, that essentially this object is a transcendental number unless there's some reason for it to be algebraic. So you could just think of it as basically being a transcendental number. On the other hand, if you look at the classical Abel's theorem, Abel's theorem would say that the sum, the abelian sum of the elliptic integral to the points of intersection with a line that's varying is constant. So that means that geometry generates a linear relation among transcendental numbers. It's a linear relation in this case with coefficient 1, but it has rational coefficients. So it's a relation among transcendental numbers, a relation defined over Q among transcendental numbers generated by geometry. More generally, if you have an algebraic, I get these things out of order. Yeah. More generally, if you have an algebraic curve defined over Q with period matrix for the holomorphic 1 forms, you can take those also to be defined over Q or a number field. Then the first Riemann bilinear relation gives you a quadratic relation on this period matrix. So if you think of the entries in the period matrix as transcendental numbers, they're the integrals of algebraic differentials defined over a number field over cycles, then you have a quadratic relation. Now, the first Riemann bilinear relation reflects the diagonal embedding of an algebraic curve in its product. It's a cycle, and it's of Hodge type 1,1. The fact that the 2, 0 part of it is 0 is exactly this bilinear relation. Okay. Grothendieck made a very beautiful, I think, sweeping conjecture that is reported on. It's the precise form in the book, several places, but in particular in the book by Andre, stating that all such relations among periods of algebraic integrals arise from geometry. And you have to explain what you mean arise from geometry, but basically it's an extension of this process here. If you go back to Abel's theorem or abelian sums, you can think of one of the terms in an abelian sum as actually being a period on a degenerate curve. So in some sense, the theorem of Abel and the relations among algebraic integrals can be fit into a larger formalism, which includes both the original form of growth index conjecture, which dealt, so to speak, with global periods, and things that would deal with addition theorems, if you like, the things coming out of Abel's theorem. Very beautiful conjecture on the sort of transcendence property of periods. And I think it certainly is related to the arithmetic aspects of much of what Pierre has done. In particular, the relation, if you have a curve defined over, or a variety defined over a number field, between this group and this group sitting in the complex cohomology. Right? You have the group generated by differentials defined over the field. You have the group of integral classes and how they relate, or rational classes, how they relate. And also the absolute Hodge classes. Those classes that are defined on the left-hand side here, which for any embedding in the complex numbers become Hodge classes. Now I'd like to talk a little bit about some of the implications of, a couple of the implications of some of the basic conjectures. Specifically, what I want to discuss is how the generalized Hodge conjecture plus the fourth of the Bloch-Beilinson conjecture gives you a way of defining the filtration on the Chow groups with the properties that are listed in the first three properties that are listed in the conjecture. In particular, the quotients are defined Hodge theoretically. This is joint work that I did with Mark Green a few years ago. The case that I'm going to start with is the case of zero cycles on an algebraic surface, configurations of points on a surface, and that was really prompted by an old observation of Norrie. So I'm going to do this going back to the admonition of the organizers in very down-to-earth concrete terms. So we'll think in general of a variety, as I said earlier, is defined by polynomial equations. And now we'll consider the relations over the rationals on the coefficients in the equation. Okay. It's finitely generated set of relations among the coefficients defined over Q. And there's the notion of a spread, a classical notion of a variety and later on of a cycle, which you get by varying the coefficients subject to the relations that these coefficients define. Okay, so these equations then with a capital A define some algebraic variety which you can take to be smooth, defined over Q. And the rational functions defined over Q are isomorphic to the original field. So the spread then of your variety you can take to be defined by the original equations, but with the coefficients now varying, subject to the relations that the original one satisfied. You think of it as a family. Okay? You're spreading it by varying the transcendentals in the field of definition. So we think of it as a family whose generic point is X. Now, coming back to the study of zero cycles on a surface, I'm going to do this in a very simple-minded way, basically looking at it as I did many, many years ago as a problem in calculus, if you like. Take a surface defined over Q and look at a zero cycle. The zero cycle will be defined not necessarily over Q, but over some field K as above, so you can take its spread, which you think of as a family of zero cycles now, defined by a variety whose function field is the field of definition of the original zero cycle. Of course, the spread is not well defined. You've chosen a model for a function field. You've chosen, again, for the spread. That variety is not well defined, so there are ambiguities. And that's the technical aspect of the story that one has to pay some attention to, but I'll come to that in a minute. The classical invariance, the degree of a zero cycle, I'll think of that as just integrating the constant function 1, which is a generator for the zeroth cohomology of the zero forms. If that's 0, then you can write the zero cycle on the surface as the boundary of a one chain, and then the Albanese, which is the Abel-Jacobi in this case, is defined by integrating holomorphic 1 forms over that chain. So that's the sort of classical invariance. Now, because of Mumford's example, conjectures of Bloch, one knew that you needed to think what additional invariance could come out of the holomorphic 2 forms. So you're given a configuration of points on a surface. You've already used the degree and the Albanese. What are you going to do? What two-dimensional things can you integrate 2 forms over? And here's where the spread comes in. So you want to find two-dimensional loci to integrate the 2 forms over. So you spread the zero cycle, and the first invariant is you take the trace relative of the differential relative to the spread. So you can think of that as pulling back the holomorphic 2 form under the mapping that takes a point in the parameter space for this family of zero cycles to what lies over it. You just sum up. It's like the trace of a function, only now it's a differential, but it works the same way. That is basically the Mumford invariant. If that's 0, then the next invariant that you look at is gotten by taking 1 cycles in the space of the spread. And I've drawn a picture here. You take a 1 cycle. As you go around that 1 cycle, you write each of the zero cycles as a boundary of a 1 chain. It traces out something like a cylinder. And you can integrate then this 2 form over this 2-dimensional object. It's the locus of these 1 chains around a 1 cycle in the spread space. I'm not going to go over it, but a little calculation shows that if the previous invariant is 0, if this one is 0, then this becomes well-defined modulo periods. Okay. Actually, I should say here that you don't just use the holomorphic 2 forms. You have to take a slightly larger space. Namely, you look in the second cohomology at the transcendental part, the perp of Duron-Severi, and take the first part of the F1 of the Hodge filtration. So it's the holomorphic 2 forms plus a little stuff of type 1, 1. You need to use all of that, not just the holomorphic 2 forms. Then if you do that, the generalized Hodge conjecture imply first that these 2 invariants are well-defined, and secondly, that they depend only on the rational equivalence class of the original zero cycle. And the fourth Bloch-Beilinson conjecture implies that if these 2 invariants are 0, then the original algebraic cycle modulo torsion is rationally equivalent to 0. So that's, if you like, one answer to what one can do beyond the Albanese to find Hodge theoretic invariance of a zero cycle. I'm thinking of this as giving Abel's theorem. 1/2 of Abel's theorem says that these 2 invariants are defined modulo rational equivalence. And the other half of Abel's theorem, the converse, is what comes out of Bloch-Beilinson 4, that if these 2 invariants are 0, then the cycle is rationally equivalent to 0. So in that sense, it's like an extension of the classical Abel's theorem. In the general case, if you assume that X is defined over the rationals and use the Kunith decomposition, so we have a variety defined, smooth variety X defined over Q, we have an algebraic cycle defined over K, and we do the spread construction. Here now you really do need to think about the ambiguities that arise in the spread construction. And the technical work is to use existing theorems about the cohomology of algebraic varieties. In particular, both the Lefschetz theorems have to be used, the primitive decomposition has to be used, and the fact that you're working with a spread. The fact that you're working with a spread comes in that if you take the family of algebraic varieties that's a spread, then a Hodge class is absolute Hodge. Hodge conjecture implies that it's an absolute Hodge, so it's invariant when you move. So taking the Kunith decomposition and taking out the ambiguities, you organize that by the following picture. This is beginning from the cohomology of X in top degree. This is in degrees 2p and 2p minus 1. And you organize, so to speak, the first half of the Kunith decomposition by this picture. So this is in degree 2p. This is in degree 2p minus 1. Now, ordinarily, when you want to take the Abel-Jacobi of a cycle, the cycle has to be homologous to 0. Here, a little remark is that in the tensor product, if the first pieces here in the fundamental class are 0, then the first pieces in the Abel-Jacobi are defined. So we saw a special case of that. Well, the classical special case is that if this is 0, that's the fundamental class, then this one, which is the Abel-Jacobi, is defined. This doesn't really enter. It's there, but you don't see it classically. You can consider it, but you don't need to. The case of 0 cycles on a surface, this was the trace, the Mumford invariant, and that being 0 was necessary that this be defined. And that's how the picture goes up the line. So the filtration on the Chow groups then that we propose is defined by this picture, the part lying under the brackets. And the successive quotients are defined Hodge theoretically by construction. And a fact is that if you have an algebraic cycle for which all of this stuff is 0, then using the generalized Hodge conjecture and the Lefschetz theory and so on, you can replace it by a rationally equivalent cycle defined over Q bar. Remember, X is defined over Q, for which the fundamental class on the product and the Abel-Jacobi on the product are 0. And then the fourth part of Bloch-Beilinson tells you this is rationally equivalent to 0, and then that implies that the original one is. So here the point is that all of what you don't see in this picture is in the ambiguity. So all that you need to consider if you have the fourth part of Bloch-Beilinson is the Hodge theoretic pieces that are in this picture here. So for example, if you have a class that's in filtration level Q plus 1, and if it's defined over a field of transcendence degree less than or equal to Q, then it's rationally equivalent to 0. That should be Q plus 2, I think. So for Q equals 0, that's the fourth part of Bloch-Beilinson, and this is just an extension. Conversely, if you have something that's in filtration level Q in the Chow, then it's a sum of cycles defined over fields of transcendence degree Q. So it's really saying that in the case of the surface or the varieties defined over Q, the filtration and transcendence level of the cycles are roughly the same. So as a small application, if you have a 0 cycle on a field, on a surface defined over Q, and if the second, on a regular surface, I left that out, of degree 0, and if the field has no holomorphic 2 forms, that's independent of which model you take for the field, then the cycle is rationally equivalent to 0. Well, that's the sort of thing that comes out of this construction. So the conclusion then is that for higher codimensions, the field of definition enters into the Hodge theory of the the Hodge theoretic invariant of the cycle. If you have a variety that's not defined over Q but defined over any field, you have to take the spread both of the variety and of the cycles. And the original argument that Mark and I had was not complete. It was completed by the referee of the paper using Morihito Saito's mixed Hodge motive papers. Since then, a more elementary argument has been given by Di Cataldo and Migliorini using the decomposition theorem of Bailenson, Bernstein, Deligne, and Gauber. So I think in general now, this picture that I did with just Kunith can be done, but you use the Leray type filtration, or the thing coming out of the decomposition theorem. And finally, I'd like to talk a little bit about some of the implications of the Hodge conjecture on the geometry of normal functions. This is an old story, normal functions going, well, as I'll say, historically back to Poincaré and then Lefschetz. And I'll give a bit of the history as I go on. The point, though, will be to say, okay, suppose that a Hodge class comes from a cycle. Then what can one say about the geometry of the normal function associated to the Hodge class? So we're going to briefly recall the definition of normal functions, the sort of classical definition, and generalize that to what I'll call extended normal functions. And then if you look at an even dimensional variety in projective space, and here we're allowing ourselves to re-embed it with higher degree as necessary, and that will come out in the argument, and blow up as needed the space of hypersurface sections. This means that you're fibering your even dimensional variety by odd dimensional subvarieties. Okay? And in this case, the primitive part of the Hodge group will be isomorphic to the extended normal functions. So to each Hodge class, there is one of these objects, extended normal function. Okay. So that'll be the first point. The second point is that an extended normal function has a singular set, and the singular set only appears in codimension 2. You don't see it when you have a one-parameter family. And moreover, if the Hodge class comes from a cycle, then if you take a high enough degree embedding in projective space, the singular set is not empty. In fact, you can describe the singular set, again, always assuming that the Hodge class comes from a cycle. You can describe it in the following way, that if you look at most, and this will be sufficient for what we're doing, at most nodal hypersurfaces, the singular set are the nodal hypersurfaces that support an algebraic subvariety of dimension n, so codimension n minus 1 here, that has non-zero intersection number with the Hodge class. So the singularities are picking up the hypersurfaces that support cycles with non-zero intersection number with the Hodge class, assuming the Hodge class itself comes from a cycle. And finally, if time permits, I want to talk a little bit about, with the normal function, pulling back some of the universal objects that are defined, the Poincaré line bundle and the theta line bundle, and relating those to the group law, or the group structure on the space of normal functions. As regards that last point, the geometric implications of a normal or of a Hodge class coming from a cycle on what the pullback of these universal bundles is not understood. I think it's an interesting question, but it's certainly not understood. An extended normal function, so this is going to be something defined over a smooth variety S. And in the variety, we have a divisor that will have what I'm going to call quasi-local normal crossings. Quasi-local normal crossing is like normal crossing, except you don't have to have that the hypersurfaces always form part of a coordinate system. You have to have transversality like here, so it's an extension of local normal crossing. And we'll look at a variation of Hodge structure of weight 2n minus 1 over the smooth part of the variety. And the most important thing is that you assume, when you have a point on the discriminant locus, that the monodromies around the branches, they're non-singular, but they don't necessarily form part of a coordinate system, but there is a transversality. The monodromies should commute. So that's quasi-local normal crossing. And then there are canonical extensions of the sort of variation of Hodge structure on the open part across the discriminant locus, done in the geometric case by Nemeti and Steenbrink, and using the work of Kitane, Kaplan-Schmidt, Kashiwara, and others in the just variation of Hodge structure case. The upshot is that the Hodge bundle, the Hodge filtration, the Gauss-Mean connection extend to the whole complete parameter space. Over the non-singular part, one has the sheaf of sections of the family of intermediate Jacobians with a condition on what happens when you locally lift a section of the quotient to the cohomology, what happens when you apply the Gauss-Mean connection. That's explained here. So classically, a normal function was a section of the sheaf of Jacobian or intermediate Jacobians over the smooth part with the property that around the point of the discriminant locus, it should lift in a single valued way. Okay. And I'll denote that sheaf by JE, sort of the extension of the sheaf of sections of intermediate Jacobians across the discriminant locus. Where these arise from geometrically is the following. If you have your variety has dimension 2n, if you have a primitive algebraic cycle, an algebraic cycle whose fundamental class is a primitive class, that means you intersect the cycle with a hyperplane section or a hypersurface section, and it's homologous to 0. If you take a Lefschetz pencil, this was the classical case, that means that you have finitely many singular fibers with one node. Then this class is still 0 on the node. You can think of it moving in an irrational equivalence. You don't change the fundamental class, and you can move it off the node. The normal function then given by the algebraic cycle is the point in the intermediate Jacobian corresponding to this algebraic cycle that's homologous to 0 on the fiber. So you think of an algebraic surface and an algebraic one cycle on it whose intersection with each fiber is a divisor of degree 0 on the algebraic curve, and take the point in the Jacobian. It's an extension of that. Over the nodal hypersurface section, you have the generalized Jacobian, which is a C-star extension of the intermediate Jacobian of the canonical desingularization. So I left a little gap there, meaning it's not compact. So these normal functions in the classical case of curves on a surface were what were used by Lefschetz. They were introduced by Poincaré exactly to study curves on a surface, and were used by Lefschetz in his proof of the 1-1 theorem. For n bigger than or equal to 2, the normal functions have been of limited use, I think, because of the failure of Jacobi inversion that I mentioned earlier. So Lefschetz said that if you have a Hodge class, it comes from a normal function. If you use Jacobi inversion with dependence on parameters, that traces out a cycle on a surface, and that was his proof of the 1-1 theorem, the idea behind it. But that doesn't work in higher dimensions because Jacobi inversion fails. So I want to talk now about what extended normal functions are and then do a few speculations. This notion of extended normal function is again something that goes back some time. I think Ron Donaghy and I worked on this many years ago. But at that time, I think that, at least for me, the foundational understanding of how a Hodge structure degenerates over a high-dimensional base wasn't really in place, and one really needs that to make sense out of this. Where is the, yeah. So the extended normal functions, an extended normal function is given by a normal function over the open smooth part. And around the discriminant locus, instead of saying it has a single valued lifting, what you say is that when you take any generator of the fundamental group of the discriminant and you analytically continue a lifting around that, and you allow yourself to multiply by an integer to get rid of torsion, that should be in the image of monodromy minus the identity of a cycle. Okay? So it's saying that you lift this normal function and you analytically continue it. That should be modulo torsion, the same thing as the monodromy applied to a cycle, but that cycle depends on which element of the local fundamental group you have. So for one-dimensional base, because you have only one generator of the local fundamental group, this turns out to always be satisfied. It's a consequence of the Clement-Schmidt exact sequence. So extended normal functions and normal functions are the same over a one-dimensional base. Okay. What the Clement-Schmidt exact sequence says is that the vanishing cycles and the invariant cycles are essentially the same up to torsion, and that's the basic fact that's used here. But over a higher dimensional base, they may be different, and that leads into an exact sheaf sequence with some quotient, which is supported in codimension 2. Okay. By definition, then, the singular set of an extended normal function is the support of what it goes into here. So the basic facts are first that a Hodge class gives an extended normal function. Okay. Classically, it was known for Lefschetz pencils that a Hodge class gave a normal function. That's something Spencer and I worked on many years ago. Then the general form of that for any family of varieties with a one-dimensional base and any singularities, but using normal functions, was done by Steve Zucker. That's the definitive form, really, for the theorem on normal functions with a one-dimensional base. And what one has to do here is to just see that you, in fact, get an extended normal function if you allow high-dimensional base. So that's the first fact. The second is that if you have a Hodge class that comes from a cycle, then the singular set of the extended normal function is not empty for high-degree hypersurface sections. Okay, so somehow having that cycle generates singularities of this extended normal function. The way it generates the singularities, roughly speaking, is to have a singular point means that the intersection of the cycle with the fiber is not homologous to 0. And that then creates the singularity for the normal function. So I think this suggests, and this is really speculation, studying the geometry of the singular set. What is its codimension? What is its fundamental class? Now, the singular, well, a normal function is a Hodge theoretic object. Okay? And the fact to a Hodge class, you have a normal function is something formulated purely Hodge theoretically. And at least in principle, the work that has been done and is currently being extended by Kato and Isui on partial compactification of the classifying spaces for Hodge structures would say that this singular set is the pullback of some boundary component in this partial compactification under an Abel-Jacobi type map. So if this Kato-Usui theory works out as it does in the classical case of families of curves on a surface, then you'll have an estimate on the codimension of the singular set. If it's non-empty, then the codimension will be bounded from above by some Hodge theoretic quantity. And I'll say what that is in the classical case in a minute. Okay. On the other hand, if the Hodge class, big F, comes from a cycle, then the singular set has an algebrogeometric description. Okay? And so it has a codimension that you can write down in terms of sheaf cohomology and so on. It's an algebrogeometric object. So that will give you some relation between an algebrogeometric object or number and a Hodge theoretic number. So let's just take the classical case of curves on a surface. Then by semi-stable reduction and so on, you can always assume the singular fibers are nodal. And the codimension of the singular locus turns out to be the number of nodes, but with a correction from the H20 of the surface. The number of nodes is the expected codimension, because when you look in the boundary of moduli of curves, you have a k nodal curve. Those are codimension k in moduli. So there's some correction of a Hodge theoretic term, of a Hodge theoretic nature. And where that comes from is that one should look not just at an isolated surface, but we should let the surface vary in moduli. So suppose the surface has some moduli space, and the surface is sitting in a big projective space. You let that vary over moduli. That's a script S, which was the small s, the regular s before. In the moduli space, you have the so-called Noether-Lefschetz locus. That's the sub-variety where you have your Hodge class remaining a Hodge class. Right? When you vary an algebraic surface, if you have a curve on the surface, it usually disappears when you move the surface. So the Hodge class usually also disappears. If you look at the sublocus of moduli, where it remains a Hodge class, this is an algebraic subvariety by Theorem, again, of Deligne, Catani, and Kaplan. And in this larger object, where you let the normal function vary also over the Noether-Lefschetz locus, then the codimension's correct. So what that suggests is that really one should not study Hodge classes, cycles, and so on for a fixed variety, but you should let the variety vary in moduli. Those parameters enter geometrically into the problem. So one can go on to analyze, in the classical case, the sort of geometry of the singularity of the normal function. It's a very nice story. Of course, the 1-1 theorem is used to help you analyze it, but knowing that, then you get a very pretty picture of what these singularities look like. You can calculate the fundamental class, things like that. If you go to higher dimensions, and if this Kato-Usui stuff works, this is a very difficult theory. I mean, it's extremely complex what they're doing. Then what's going to come out would be some estimate saying an algebrogeometric number, a cohomology, dimension of a cohomology group, is bounded by a Hodge theoretic number. And I don't know what that inequality is going to be, but if you just play around with it, you get some feeling for the sort of thing it's going to be. And what it's doing is showing that when you get in higher dimensions, codimension, you get, for Hodge theoretic reasons, correction terms to dimension counts that at least I'd never thought of in codimension 1. So I'll mention a simple one here and close with that. If you go back to the case of algebraic surfaces and look at the moduli of algebraic surfaces, the expected codimension of the Noether-Lefschetz locus, the locus where a class remains of type 1-1, is the number of conditions that a class be of type 1-1, which is the Hodge number H20. So expected here means that that's what a dimension count would give you at first sight, and that's usually true for surfaces, but not always. So if you take, for example, a general surface in surfaces in P3, this works. Okay. Now go up to dimension 4-dimensional variety. Then the expected codimension of the Noether-Lefschetz-Noether should be the number of conditions to be a Hodge class, okay, 4, 0 plus 3, 1. But that's wrong, because if you look at the differential of the defining equations, they all land in 3, 1. So your refined estimate is 3, 1. But that's wrong. If you look at the tangent vectors, the things in H1 of theta, sorry for the messy overhead, that annihilate the Hodge class, and look at the cup product of those in the H31 part, then the right number here for the expected codimension has this correction. This is a second order correction. The first correction was first order, and this is a second order correction, and it goes no further. So there's some phenomenon coming at second order in the geometry of these loci, of Hodge loci, if you like, that's entering in higher codimension. And it's that sort of thing that if one just guesses what you would get in this inequality, seem to turn up. So to conclude, I mentioned, because I think it's kind of a pretty little fact, what happens when you take these normal functions and you pull back universal line bundles. So you have polarized abelian varieties or polarized complex tori. They have line bundles on them. You have line bundle stacks, if you like, but you can make sense out of their Chern classes and so on. And only for Lefschetz pencils, it's not known when you get things that are more interesting. If you take the pullback of the theta bundle under the sum, and you take this relation that looks like the group law on an elliptic curve, then that gives you the cup product. These are cohomology classes in the middle dimension, so their cup product is an integer. These are line bundles on P1, so they have a degree. That's the relation. So it's reminiscent of the group law on 0 cycles on an elliptic curve. Or if you pull back the Poincare line bundle, remember that's on the product of something with itself, under the product of two normal functions, you again get this cup product of zeta and zeta prime. And I think that's interesting for several reasons, but one of them is that if you look, let's just do classically, look at surfaces in P3 and look at a Hodge class on a surface. We know it's an algebraic cycle. What is the least degree surface you can get that will support that cycle? The least degree curve you can get that will support the cycle. And the lower bound is given by the self-intersection number of the Hodge class with itself, or minus that, because this is a primitive class. So zeta squared, or the products, if you like, that number is, I think, a critical number in the sort of geometry that's floating around for these normal functions. So in conclusion then, I think for those Hodge classes that come from cycles, there seems to be some interesting geometry in its normal function. It's not at all like the classical picture where you had inversion and you immediately got a nice construction. But going to the singular set seems to give some geometry, or may give some geometry in this object. So thank you.
Thank you for marvelously adhering to the directive. Are there any questions or comments?
Yeah.
What if you want something about Generalized and diverter with normal crossing? Because you can blow up and then it would be diverter with normal
Right,
crossing.
and that's one of the issues in the theory, that you blow up and these singularities don't behave well under blowing up. So if you want to capture them this way, you need to restrict. So you look at a quartic surface containing a line, and you see the picture there is very clear.
And can you repeat the definition of this generalization? So any two of the diverters would be transversal?
That's right, yeah.
All
So what you want is a transverse slice, any subset less than or equal to a codimension meet transversely. And you need commuting monodromy. The commuting monodromy is the essential part. And the reason is what one is looking here, if you think of nodal hypersurfaces, the mapping of nodal hypersurfaces lying in X to moduli of the hypersurfaces is not transverse at the boundary. And it's that non-transversality that's coming in. The non-transversality for the case of the classical case is exactly the H20 number of the surface. That's how non-transverse these nodal curves meet the boundary of moduli of curves. And for higher dimensions, you get into the second order behavior. So if you're going to do intersection theory, in this it's going to be something quite different from what one has had classically.
Any other questions or comments? Okay, let's thank the speaker again. It's great.
Yeah, okay.